All right, welcome back. Okay, so last time we gave all the different definitions of singularities of the minimal model program. Let's recap them and all the relations between them, and then I need to make one slight correction. So we have our log pair x comma delta. And let's just denote the discrepancy of x comma delta by just a, just to make the table a little easier. So we have these various discrepancy conditions, like a was greater than 0. Let me recap them in the case that delta is 0 first. So when a was bigger than 0, we said this is terminal. And then if a is greater than or equal to 0, we have canonical. And then if a is greater than -1 and in general the round down of delta is 0, then we have KLT, but on this side, we're just going to consider quickly the case where the boundary is actually 0. And then we have, on this side, KLT is the same as PLT because there is no boundary. So the condition is obviously satisfied, which is the same as DLT, which was this more complicated notion of log terminal, but again, with no boundary, it's equivalent. And then all of this implies log canonical. Okay, so these implications are true when there's no boundary, and so for that reason, we'll just all three of these are sometimes just called log terminal when there's no boundary. So if you ever see let x be log terminal, then it just means there's no boundary and this discrepancy condition is satisfied. But when there is a boundary, it's slightly more complicated. There's just one implication that I said that's not true, and it's exactly this canonical implies KLT one because of this round down condition. So in the case where the boundary is not empty, so the general case, we'll write on this side, we have terminal implies canonical, and terminal implies KLT. But canonical does not necessarily imply KLT, just because you can't have a pair with canonical singularities where the divisor is coefficient 1, and this exactly happens when you have a smooth variety and a smooth divisor. So if you have a smooth variety and a smooth divisor, then this round down condition isn't satisfied because you have coefficient 1, but all the discrepancies are actually greater than or equal to 0. So another way to think of it is that for the KLT condition, you really want to look at not just the discrepancy, but the total discrepancy. I.e., when you look at all divisors and not just exceptional divisors. So you can rephrase this KLT condition as saying the total discrepancy is greater than -1, and that exactly tells you the coefficients have to be smaller than 1. But then canonical does imply PLT, and so does KLT. And then this implies DLT, which implies log canonical, and all of these arrows are actually just one-way arrows in the whenever you have a non-empty boundary. And I should say, like this example where canonical is in KLT, the only as soon as you if x is smooth and you have singularities along your divisor, then canonical will force the coefficients to be smaller as soon as you get singularities on your divisor, because then you have to actually do some blowups and the multiplicity matters. So it's only the case where the divisor itself is smooth that you have this slight issue. Okay, so and let me recall the definition of DLT that we gave, and I'll write it here. So we said DLT was the condition that there exists a z in X closed, such that the pair X minus Z delta minus Z is normal crossings. So simple normal crossings. It's really important. It has to be simple normal crossings, and the discrepancies are greater than -1 for any E lying over Z. Yeah. So the definition is saying you have some locus where you have these discrepancies that are like the KLT case or the PLT case, but then outside of that locus, maybe you have worse discrepancies. Maybe you have strictly log canonical, but those strictly log canonical ones are just coming from normal crossings, so they're easier to handle from simple normal crossings. So let me give a few continuity properties about how these singularity conditions behave under perturbations. And these are basically just from the definition. So let's say x comma delta is a log pair, and D is effective and Q Cartier. So the general question is just if you perturb your delta by adding some epsilon D, how do these singularity conditions behave? So first condition, if x delta plus D is any of the conditions, let's say terminal, respectively, canonical, KLT, PLT, DLT, but in every time in this in what's following, every time we talk about DLT, we'll add the extra condition that delta is effective. That was part of the definition of DLT. Actually, I should have said. So for all these other ones, you can talk about these singularities with your boundary having negative coefficients, even though that almost never actually comes up. But the theory still makes sense. For DLT, you really want that the coefficients of delta are between 0 and 1, only for the DLT case. So yeah, so in what follows, assume effective whenever we're talking about DLT. Otherwise, you don't have to assume effective, but in all applications, delta is effective. So it's not too big of a deal. So if you have that x comma delta plus D is any of the singularity conditions where D is some effective divisor that you've added, then x comma delta also has these singularities. So this says that that if you subtract something, then the singularities can't get worse. That's essentially what it's saying. Which just comes from this lemma from 2 classes ago that I didn't prove. I left as an exercise that when you add an effective divisor, the discrepancies get smaller. So when you remove an effective divisor, the discrepancies get better. 2, if x delta is terminal or respectively KLT, then x delta plus epsilon D is also terminal or KLT. For epsilon small enough. And so this is one of the nice things about KLT is that it's really an open condition that you can perturb your divisor by some small epsilon and you still lie within KLT. For PLT and DLT, it's a little more complicated because you need to control the places where the coefficients are 1. So this is what's nice about the condition of rounding down being 0 for KLT. It doesn't matter what you add as long as the coefficient's small enough, you won't break the discrepancies. But for PLT and DLT, you need to be a little careful because you might have some coefficient with divisor 1 and you can't add anything to that divisor without making negative discrepancies. Essentially because of that example where we showed that if you have a divisor whose coefficient is strictly smaller than -1 in the discrepancy, then you actually have discrepancies that are minus infinity. So as soon as you have this divisor that has coefficient 1, which is allowed in the PLT and DLT case, you have to make sure that you're not adding anything to it. And so for PLT and DLT, the analog is this is true as long as you are careful about what divisor you add. So if x comma delta is PLT and D doesn't share any components with delta, then x comma delta plus epsilon D is PLT for small enough epsilon. And similarly for DLT, the easiest condition to try to impose is that the support of D is contained in the divisors where that have small coefficients. So basically, so if I look at only the divisors that have coefficient less than 1, then I'm allowed to perturb those and still be DLT. And then finally, the last one is saying that the canonical ones, that canonical and log canonical, are like the closures of the terminal ones. So let me write it for log canonical, for just canonical first. So if x delta is terminal, then x comma delta is canonical, x comma delta plus D. So then when we add this extra divisor, we get something canonical if and only if x delta plus epsilon D, or plus CD now, because it doesn't have to be infinitesimally small, plus CD is terminal for all C less than 1. So it's saying that if you add something, it's something that's actually canonical, then any smaller number, as soon as I take 1 minus epsilon times D, I actually have to be terminal. So kind of canonical is the boundary of terminal. Let me modify this for the log case. So in the log case, if we assume that the pair is KLT, PLT, or DLT, then x comma delta plus D is log canonical. So in any of the three log terminal cases, then when we add D, we get something log canonical if and only if the pair delta plus CD is KLT, PLT, or DLT for all C less than 1. So if we have something KLT, then when we add D, we get something log canonical if and only if whenever we add 1 minus epsilon D, we get something that's still KLT. And similarly for PLT and DLT. Okay, a few more propositions and definitions before I can do a bunch of examples. So here are two properties of DLT, and I waited till after continuity results to state them because they really use the continuity results, even though I won't write down the proofs in full detail. So the first one, analogous to the other ones where we showed that you only need to check one resolution to check any of the other properties. The same is true for DLT. So x comma delta is DLT if and only if there exists this closed subset Z such that x minus Z delta minus Z is S and C, and there exists a resolution such that the discrepancy of any prime divisor is greater than -1 for any P lying in F inverse of Z. So again, this is saying that your DLT if you have this subset away from which your simple normal crossings, and then you have a resolution where every discrepancy over that Z is greater than -1. So you only need to check one resolution rather than the definition, which said just any exceptional over that Z had to have discrepancy greater than -1. Okay, and the proof of this essentially is like we've done before, where you pick a resolution and you put the right divisor upstairs so that the discrepancies downstairs are the same as the discrepancies upstairs. And now you use that you have this extra wiggle room that all your all the divisors inside of F inverse of Z have to have coefficient strictly smaller than 1 in your divisor upstairs, in your boundary divisor upstairs, because of the definition of DLT. And so you have this extra wiggle room where you can add any, some small epsilon of these divisors and still get something that's log canonical by these continuity results. But when you add this epsilon, you make the discrepancy strictly smaller. And so when you make the discrepancy strictly smaller and still get something log canonical, then all the discrepancies you had to have been strictly bigger than -1 over those divisors. So it uses this kind of perturbation, but essentially the same idea as the other versions of this proposition. A more involved one, which is maybe the easiest definition of DLT to digest, but maybe a little harder to work with, is that x comma delta is DLT if and only if there exists a log resolution f from y to x such that the discrepancies are greater than -1 for all f exceptional divisors. So this one is saying that your DLT, if and only if there exists a resolution where the discrepancies on all exceptional divisors of that resolution are greater than -1, here you actually have to be careful about the resolution you pick. You can't just pick any resolution, because if you're in the normal crossings locus away from this Z, and you start blowing up at some point where two of your SNC divisors intersect, then you'll get a discrepancy that's -1 for that exceptional. And so the content of 2 is that when you're doing resolution of singularities, you can actually control the resolution that you build, so you only resolve the z. You only have to blow up inside of the z because you're already SNC outside of z. And so to prove the equivalence in 2, you actually need to control how you resolve singularities, which is why it's a more subtle definition for DLT than the previous one. And then a property, if we know that x comma delta is DLT, then it's KLT if and only if the round down is 0. So it's saying that the gap between KLT and DLT is this round down condition. So let x comma delta be a log pair. Then a non-KLT place of x comma delta is a divisor p lying over x. So some prime divisor p lying over x with discrepancy less than or equal to -1. And then a non-KLT center is a closed subvariety of x comma delta that's the image of one of these divisors. And then finally, if x comma delta happens to be log canonical, then we call the non-KLT centers log canonical centers. Because that's the place where the singularities are strictly log canonical rather than KLT. Is this too low? Like, where's the cutoff? Oh, that's good. Okay. So often in literature, you'll see log canonical center, but that definition only makes sense when you know your pair is actually log canonical. So it's good to kind of define both. And then some notation will denote by n KLT the closed subvariety, which is the union of all non-KLT centers. So of course here, we're using the fact that you can test KLT on one particular resolution to know that there are only finitely many of these centers. Okay, so any questions about that definition? And a lot of the game here will be that like we can control what's happening away from the non-KLT locus using vanishing theorems that will start proving hopefully in like 10 minutes. And then you need to understand what's happening at these log canonical centers. So a lot of the game of working with log canonical varieties is that you have some linear series you want to understand, some divisor you want to understand, and you need to control what it looks like on the log canonical centers, which is where things can go wrong. And there you need to use some kind of induction methods to understand those. Okay, and then finally the last definition. This is the log canonical threshold. So we have x delta our log pair. D is some effective Q-Cartier divisor. And let's suppose that x delta is log canonical. Then the log canonical threshold of x comma delta with respect to D is the supremum of t greater than 0 such that x delta plus td is log canonical. And by our previous continuity results, we know that for any t smaller than the threshold, like let's say that x comma delta is KLT, for example, instead of strictly log canonical, let's say we're in the nicer situation where it's KLT, then we'll know that for any t that's smaller than the threshold, this new pair is also KLT. And so this kind of threshold is just where you exactly hit this log canonical boundary, this closure of the KLT locus. And here, so a couple of remarks. One is just that all these definitions make sense for R divisors, as long as you assume the appropriate Cartier R Cartier for Kx plus D. And a priori, this T is just a real number because it's the supremum of some set. But the second remark is that if delta and D are both Q divisors, then T is actually rational. And maybe I should say here again, these definitions make sense for R divisors as long as you assume all the appropriate things are R Cartier. Basically, anytime we had to assume something was Q Cartier, assume it's R Cartier. And this last part, why is this log canonical threshold rational? If the divisors are rational, you can just compute it using a resolution. So you write down a resolution, you compute the discrepancies, and you find a formula in terms of minimums of some rational expressions for this log canonical threshold. So I'll leave that as an exercise. Okay, questions? Okay, let's draw some examples. So in all these examples, X will be P2, just because it's the easiest thing to draw. Well, in all the examples except the last one. So let's say we have P2, comma, an irreducible nodal cubic. Then, and with coefficient 1. So D is really this irreducible nodal cubic, and the coefficients are 1. Then this is log canonical, but it's not DLT. So to see its log canonical, well, you can take a simple normal crossings resolution by blowing up that node point. And then the discrepancy of that divisor is -1. And everywhere else, you're just have x with a smooth divisor. So any other discrepancies of any other blowups are strictly bigger than -1. But it's not DLT because there's no locus where this divisor is normal crossings, because it has simple normal crossing. Sorry, it is normal crossings, but it's not simple normal crossings because it has a self intersection. Now we can look at P2 with D1 plus D2, where D1 and D2 are the nodal union of just the axes. Then in this case, we have something that's DLT because it's actually simple normal crossings, but not a PLT. Again, because if you blow up that node point, then you have a discrepancy that's strictly -1. So in both these cases, the non-KLT locus is this node. We can get something that's PLT by just decreasing the coefficients on one of these divisors. So if we look at P2 comma D1 plus 1 minus epsilon D2, then this is PLT, but it's not KLT because there's still this divisor D1 with coefficient 1. But it's PLT because as soon as we decrease this coefficient by epsilon, then that exceptional over that exceptional that gave us a discrepancy -1 now has a discrepancy -1 plus epsilon as soon as we decrease this. And then finally, in the same sequence, we can just look at P2 comma A D1 plus B D2 for A and B both strictly smaller than 1. Then this is something that's KLT. Now we have all the discrepancies are greater than -1 and all the coefficients are smaller than 1. Okay, so those are some kind of basic examples, but it really the most important takeaway is that the DLT condition, the thing that makes it so subtle is that it's a global condition. Locally, these two pictures, 1 and 2, look exactly the same locally around the non-KLT center. Also I should say here in these cases actually the non-KLT center is this whole, I guess the whole thing because it has coefficient 1. But anyway, so right, so this DLT condition, the thing that makes it subtle is that it's a global condition, while all the other discrepancy conditions are really local. They're really local around each of the centers of each divisor. They're a condition that says at every non-KLT thing. Okay. Okay, more interesting example. Let's look at P2 comma delta, where delta is some constant times the cuspidal cubic. And now we can try to compute when is this KLT, when is it log canonical. And so to do that, we write down a resolution. So I claim that there's a resolution. If you blow up 3 times, then we get a log resolution where the picture looks as follows. So we have a component corresponding to our D. And then we have a bunch of exceptional components. One we'll call E1, and then some other exceptional components like this, E2 and E3. And now EI squared is minus I. We can compute that from these three blowups, and then we can compute that f upper star of D is the strict transform plus 2e3 plus 3e2 plus 6e1. So those are the multiplicities, and then f upper star k is ky minus e3 minus 2e2 and minus 4e1. And again, this is from using the formula that when you blow up once, you have to subtract one copy of the exceptional, but then when you pull back again, you have to subtract another copy of the exceptional plus some contribution coming from the first copy that you subtracted, because these blowups are all kind of on exceptionals. And so putting this all together, we get that I'm going to write it in the log form rather than the regular discrepancy form. That this log canonical divisor is equal to the pullback plus the following coefficients. We have 2 minus 2c times e3 plus 3 minus 3c times e2 plus 5 minus 6c times e1. And the reason I wrote it this way in the log form with log discrepancies is just because I find it easier to compute this way, because you write it this way and then you can solve for the coefficient on the other side by using adjunction, by kind of smashing each side with EI and using the fact that KY plus EI dot EI is the canonical of EI. And so what this tells us is that, so with log discrepancies, we need the log discrepancy to be greater than 0 or greater than or equal to 0 for KLT and log canonical. And so this tells us that the log canonical threshold of P2 with no boundary relative to this cusp is 5/6, because that's when the log discrepancy becomes 0, or the usual discrepancy becomes -1, and that the pair x comma CD is KLT for any C strictly smaller than 5/6. And so we see here the cusp is a more complicated singularity than a node, and so it has a smaller log canonical threshold and a smaller range where it's KLT. So the more singular the divisor gets, the smaller coefficient you need to make it KLT. Okay, and then one more example. This was 5. One more example where we're not on P2. Well, let's say that X is this cone over a rational normal curve, which we discussed a few classes ago. And let's say that D is one of the lines through the cone point. And so we're looking at the pair X comma delta, where delta equals CD. This is the cone over degree n rational normal curve. It has a resolution that's like this total space of the line bundle O minus n, and so E squared is minus n, and then using that in adjunction, we can just compute. I won't write down all the various steps. I'll just write down the final computation. So we get the ky plus E plus strict transform of delta is f upper star kx plus delta plus 2 minus c over n e. And this 2, it comes from adjunction. The way we're going to compute this coefficient is by using that e as a rational curve. So ky plus e dot e is minus 2. So that's where this 2 comes from. The n comes from the e squared is minus n. The c comes from the coefficient on d. And yeah, so what's the upshot here? The upshot is that actually x comma delta is KLT for all c less than 1. So of course, c needs to be less than 1 for the round down condition. And this discrepancy, this 2 minus c over n, is always going to be strictly smaller than 1 as long as c is less than or equal to 1, in fact. And so it's KLT for all c less than 1, and then it's PLT for c equals to 1. Because at c equals to 1, the discrepancy is still bigger. The log discrepancy is still bigger than 0, or the discrepancy is bigger than -1. And so this gives us an example of something that's PLT at the log canonical threshold. So as soon as you go above 1, you're not even log canonical anymore because you have this divisor with large coefficient. But at the log canonical threshold, it's actually still just PLT. And here, say this. Okay. Next, we're going to move on to vanishing theorems. So, so our next goal is to prove a sequence of stronger and stronger vanishing theorems, starting with the Kodaira vanishing theorem. So in the end, we want to prove at least a vanishing theorem for KLT pairs, but all of these different vanishing theorems reduce to the smooth case and reduce the Kodaira vanishing theorem. So we'll start there. So the theorem says that, and I think this came up in the surfaces portion where we just used it without proof, but I'll recap the theorem. So let X be smooth projective. And here I'm really gonna, even though I said the whole class is over the complex numbers, I really want to emphasize that this is over the complex numbers. Though other characteristic zero fields are okay by standard reductions to the complex numbers, but the proof is really a complex thing. And let's say L is an ample Cartier divisor. Then the cohomology of X with coefficients in Kx plus L is 0 for all I greater than 0. Or Serre dually, we could say that the cohomology of X with coefficients in OX of minus L is 0 for I strictly less than N, where N is the dimension. So throughout all these proofs, we'll use N for the dimension of X. Okay, so that's the theorem. These divisors of the form Kx plus L. So when L is actually our delta, our boundary for some log canonical pair, then we call it the log canonical divisor. But more generally, when you just have this L and you're looking at cohomology of Kx plus L, these are often called adjoint divisors. And because they appear so frequently in these vanishing theorems, they have a name. Or adjoint linear series. Okay, so let's just start with the proof, but with the remark that this is actually, not only do we really need to use C in the proof, but this theorem is actually false in positive characteristic. Okay, so the first step is we'll do it for the slightly easier case where L itself is actually an effective ample divisor. So L a priori is just some ample divisor, but not necessarily effective. Let's assume that L is some smooth effective divisor. So in this case, we have the standard ideal sequence. And now we can take cohomology, and so we're going to prove this Serre dual version where we want to show that hi is 0 for all I less than the dimension. So we'll take cohomology. What do we get? We get hi minus 1 OX maps to hi minus 1 OH maps to hi of the thing we want to show is 0 in that range goes to hi OX and goes to hi of OH. And these maps, what are they? They're restriction maps. So let me just call them restriction I minus 1 and restriction I. They're the maps on cohomology coming from restricting the structure sheaf from X to H. So what do we want to show? We want to show that all these maps, all these restriction maps are isomorphisms, except possibly at dimension n minus 1, where it's okay to be injective because we're only proving the vanishing for I strictly less than n. We don't care about the vanishing. I mean, the vanishing just isn't true when I is equal to n. So we want the restrictions to be isomorphisms for I strictly less than n minus 1 and injective for I equal minus 1. That's equivalent to the statement that we're trying to prove in this case. And this is essentially the statement of the Lefschetz hyperplane theorem. And so this is where we're really using that we're over the complex numbers, and so we have topology. So the usual form of Lefschetz hyperplane tells you that in this setting where H is a smooth ample divisor, and X is projective, then the restriction maps on singular cohomology are isomorphisms in the range I less than n minus 1, and they're injective for I equals n minus 1. So it's a very important and famous classical result. I won't give the proof, but I'll just say a few words. What comes up is the fact that since H is ample, then the complement of H is an affine variety. And then there's a long exact sequence that relates the cohomology of the affine complement to this restriction map on the cohomology of X and H. And then you can use a famous result that says that the cohomology of complex affine varieties are half the dimension that you'd expect. That complex affine varieties have the homotopy type of a CW complex of half the real dimension. And so that kills off the co-kernels and kernels of these restriction maps in the right degrees. And that's how you get it exactly for half of the degrees minus 1 where you have singular cohomology, because the singular cohomology goes up to the real dimension 2n, and so we get it for these in these degrees because the complement has half the cohomology that you'd expect. Okay, but then we use some Hodge theory because we don't care about singular cohomology, we care about the cohomology of O. But Hodge theory tells us that this is the direct sum of HP omega Q X, or maybe I really should get in the habit of writing it the other way because that's the convention with HPQ. where P plus Q is equal to I, and this is the same thing for H. And then the only input left is that the restriction map for singular cohomology is really functorial with the restriction maps for these coherent cohomologies. That this diagram, where here I put the direct sum of restrictions for HPQ, really commutes with this restriction for singular cohomology. So that's the kind of naturality of the Hodge decomposition. And so this tells us that, well, it tells us that these restrictions on Hodge groups they're isomorphisms for I less than, for P plus Q less than n minus 1, and injective for P plus Q equaling to n minus 1. But these restriction maps, as a special case, are these restrictions on O, because these are the cases where P is 0. And so we get our Kodaira vanishing in this case by this long exact sequence as we observed above. Now step 2, we want to reduce to this case. So we want to have some L that's not necessarily a smooth effective divisor, but is just some divisor that happens to be ample. And we want to reduce to this ample case, to this smooth case using cyclic covers. So this is a trick that already came up when we were classifying surfaces. And it's just a really key and useful technique in proving these vanishing theorems. So it'll come up over and over again. But we need something slightly more general. When we were classifying surfaces, we wrote down the cyclic cover construction for where you get unramified cyclic covers associated to torsion bundles. And now more generally, if you just have any line bundle L, and let's say we have a section of L to the tensor M. So in our previous setting, we had actually a non-vanishing section. So S was actually an isomorphism. Now we have something more general, just any section, maybe non-zero. And let's say D is the divisor associated to the section. Then we can construct a cyclic cover that's branched along D, and that's an M-fold cyclic cover as follows. So we want to define an algebra to take spec of. And it looks exactly the same as before. Our algebra is the sum from I equals 0 to m minus 1 of the line bundles L to the minus I. And we want to define a multiplication that's compatible with the grading. And so for that, we look at the usual multiplication map on this line bundle. But now L to the minus I minus J is not actually one of the terms in our algebra. So we need to shift by this section S to get back to something in degree between 0 and m minus 1. So we apply S tensor the identity to get something in L to the m minus I minus j. And now if I and j are between 0 and m minus 1, then m minus I minus j will be in that range. And so this gives us a multiplication on this algebra A. And so now we'll just define x and d to be spec over x, this relative spec of this algebra ALS, and this should be an M here. Okay, so that's just the abstract definition. We constructed an algebra, took its spec. That's some scheme that's affine over x. And the algebra's finite coherence was actually finite over x. But we really want to understand it a little better. So the key point is that locally, what is this algebra? If we trivialize everything, then this just looks like OU adjoin a single generator Z. So where the degree I term is generated by Z to the I, but now we're quotienting out by this multiplication is exactly saying that Z to the M is equal to our section S. And so locally, this algebra is just this algebra OU adjoin Z mod Z to the M minus S. And so what is this thing? It's a cyclic cover of degree M. So by that I mean it has a action by the mth roots of unity. So it's a Galois extension of algebras with Galois group mu m, and it's ramified exactly where S vanishes. And it's totally ramified because it's Z to the M equals S. So the upshot is that this map is an M-fold cyclic cover that is totally ramified over D. And so if we look at P upper star D, then that's going to be equal to M times some reduced divisor dm, where the reduced divisor is the vanishing of Z. So the vanishing of S is M times the vanishing of Z. And in terms of line bundles, P upper star of L is now isomorphic to OX of dm. So the point is L itself was not necessarily effective, but L to the tensor M was. And so now we've extracted an mth root of L. We've extracted an effective divisor for L after taking an mth root. The other observations are that the projection map from dm to D is actually an isomorphism. Again, that comes from looking at this algebra description in terms of affine coordinates, because if we look at the reduced vanishing of S, well, that's just the same as OU mod S, just from this algebra. So this is an isomorphism, and so P lower star dm is D. And then finally, just from the definition of relative spec, P lower star of OX MD is this algebra that we took spec of. Some formal property of relative spec. Okay. I said finally, but there's actually one more fact, again, coming from just looking at this local description. If X comma D is a smooth pair, so if X is smooth and D is also smooth, then that implies that XMD comma DM is also a smooth pair. And again, that just comes from this local description. So if X is smooth, then after completing, we can write down this OU as some polynomial ring, and then we're joining one more variable and modding out by Z to the M minus S, where S is a smooth, cuts out some smooth locus in the polynomials, x1 through xn, and so then by taking derivatives of this Z to the M minus S, you see that this guy is also smooth. Okay, so now our strategy is to say we have this ample divisor. that's not necessarily an effective smooth divisor. But because it's ample, we know that some large enough power is very ample. And so we can take a generic hyperplane section of that large enough power, and that's a smooth divisor. And so then we're going to apply this root construction to our L to reduce to the case of step one. So now we're back to our setting. And then in step three, we're going to show the vanishing upstairs on a root. So now we're in our setting of x comma L as in the hypotheses. And we pick some very ample smooth hyperplane section of a large multiple. And now we construct the cyclic cover. So let's just denote x prime as the cyclic cover, the m-fold cyclic cover branched along D. And right. And let's just denote by D prime the divisor dm, the root of D. So now D prime is isomorphic to D abstractly. So in particular, it's a smooth divisor, but also P upper star of L is linearly equivalent to this D prime. And so that's actually ample because it's the pullback of some ample divisor by some finite map. So we have the smooth ample divisor. We also know that x prime is smooth. And so on x prime with respect to D prime, we have the vanishing by step one. Then this tells us, so hi x prime, O x prime minus D prime is 0 for I less than n. And the dimension of x prime and x are the same because this P is finite. But this, we just said that P upper star L is D prime. So this is the same as saying that hi of x prime with coefficients in P upper star of the divisor we care about is 0. Okay, so what we've shown is that there's some m-fold cyclic cover where when we pull back our divisor, then we have vanishing for that divisor on this cyclic cover. And now the last step is to show that that implies vanishing on our original x. Okay, and so now since P is finite, then we know that the higher push forwards are just 0. And so we can compute cohomology upstairs or downstairs. So then for any locally free sheaf, we have that hi of x prime with coefficients in P upper star E is the same as hi on x with coefficients in P lower star, P upper star E. But now by projection formula, this is the same as hi x with coefficients in E tensor P lower star OX prime. But then we know what P lower star OX prime is. It's this direct sum that we took spec of. It's this direct sum of L to the minus i's. And because cohomology of a direct sum is direct sum of the cohomologies, we can just write that this whole thing is equal to direct sum from I equals 0 to m minus 1 of hi with coefficients in E twisted down by RL. Right, and so in particular, now we apply this to E equals OX minus L, and so by step 3, the left-hand side is 0, and so that implies that each of these summands is 0. So in particular, that implies that HIX comma E itself, or in this case OX minus L, is 0 because that's the special case where I equals 0. Oh no, I used I and I both times. Sorry about that. Let me make this a K. There we go. So that's a special case where K is 0 is when you just have the E itself. Okay, so that's that completes the proof of the classical Kodaira vanishing theorem. Are there any questions? Okay. So in the last few minutes, let me give a generalization that I won't do the full proof of, but it's just useful to know. I don't think it's going to come up again in this class, but maybe it will. Not totally sure. So Kodaira, Akizuki, Nakano vanishing. Sometimes just called Nakano vanishing, but it generalizes Kodaira vanishing, and then I think Akizuki and Nakano had a paper on it together. So same assumptions, X is smooth projective. I'm going to use line bundle notation. L is an ample line bundle. Then we have the following vanishing. If we take HQ of omega px tensor L, then this is 0 for p plus q strictly smaller, strictly bigger than n. Or by Serre duality, this is equivalent to saying that HQ x omega p x tensor L inverse is 0 for p plus q smaller than n. And this is generalization because if p equals 0 here, then we get, if p equals n here, then we get the usual Kodaira vanishing, because if p is n, then p plus q is greater than n is just saying that q is greater than 0. So then we get Kodaira vanishing in its first form. And similarly on the Serre dual side, this is when p equals 0. That's the same as Kodaira vanishing in its Serre dual form. So this is a generalization to these more general sheaves where you don't just take the canonical, but you take any of these intermediate sheaves of differentials. But the proof is kind of the same strategy. We saw up here that in the Lefschetz theorem, we actually do have that these restrictions are surjective for any of these cohomologies of sheaves of differentials, or isomorphisms and injective in the right ranges. So basically the only difference is you need to replace this exact sequence in the case where you actually have a smooth divisor you need to replace this exact sequence with some exact sequence that involves omegas instead of just O. So I'll just write down proof sketch. Same strategy, but use the following two exact sequences to relate cohomology of these omega sheaves with cohomology on D. So we have a sequence that's like with these sheaves of logarithmic differentials that I briefly mentioned a few classes ago. So these are sheaves that locally are generated by things of the form dz1 over z and then dz2 through dzn, where d is the vanishing of z1. And what is this map? This map is the residue map that takes some differential form with poles to its residue, just the usual complex analysis residue. And since it eats up one of the poles, that's why you get something p minus 1. And then the second one, you need to have restriction somehow. So the restriction fits in where if you look at omega px log d twisted down by d, this sits inside of omega px, and this is the kernel of restriction to omega p, like that. So the strategy is the first exact sequence plus induction on the dimension reduces the statement to proving something about omega p log. And now this omega p log, when you twist down, becomes the kernel of restriction. So now the second exact sequence relates you back to the case of Lefschetz hyperplane theorem. And so these two exact sequences plus induction prove it in the case where your divisor is actually a smooth ample. And then you do the same exact cyclic cover, but now you need to understand how the logarithmic differentials change on cyclic covers. And so the key fact 3 is just that on a cyclic cover, p upper star of logarithmic differentials downstairs are logarithmic differentials upstairs. And this is a local computation just in terms of the equations. And so that lets you carry out the last step, which was reducing it to the cyclic cover. And so we get this KAN vanishing. And the last remark I want to make, sorry I went a bit over, is that all of this is reversible. And it's actually true that this KAN vanishing is equivalent to the holomorphic Lefschetz hyperplane theorem. It's actually equivalent to the fact that the restriction maps on Hodge groups are satisfy Lefschetz hyperplane theorem. And so there's another strategy for all of this story where you try to prove this vanishing originally directly, again using the cyclic cover tricks, and then use that to prove Lefschetz hyperplane theorem. But either way, you have to use some topology. So in this other case, you have to study some topology of some local systems. And so either way, you can't get around the fact that it's really a statement about complex numbers. Okay, I'll stop there. Sorry for going a bit over.